hello Spencer, hello Connor. We are going to practice the collective grading. I hope you like this idea. And then, if time allows, and I hope it allows, we'll go over the overview of research projects. So, everyone should have received the invitation to serve as appointed grader, right? Did you get it?
Yeah.
And you accepted the rule. Okay, so we keep the identity of the grader and the gradee secret, just in case someone is sensitive. And I'm going to announce the answer key. If you are online and you didn't get the invitation, let me know. I can forward it. I was just postponing the. I was trying to send the materials only after the grader has submitted his or her own work. So here's the schedule: 10, 25, 25, 30, 10. It should, from 1 to 5, should give 100%. Let's check. 50, 60,
90, 100.
yes. And the 40 just gives safety cushion so that everyone feels comfortable. I glanced through and you guys are performing well and just making sure that everyone on the same page. So when you are done with grading, please add numbers together to the front page so that it is easier to collect the grade. So number 1. Some of you took benefit of computerized tools, which is in modern world is completely legitimate. But what if you need to do physical chemistry on the inhabited island without computers? One just takes the polynomial, finds the roots, explores where it changes the sign. So the one here, one can put x out of brackets, and then it's product of two polynomials, x and this 3 minus 4 x squared, right? So one finds the x has root at 0. This one has roots of plus minus square root of 3 over 2. And then everything else is multiplied by the bell of Gaussian distribution, which is always positive. And then one checks for the signs, which would be minus minus gives plus, minus plus gives minus, plus minus. So it should be a stuff that oscillates and then goes to 0 at the infinity 10 points. The Rodriguez formula is the way to generate polynomials by just applying derivatives. So it's like 25, and I think everyone did it correctly, or at least same as I did. So first order, if one doesn't do any derivative, this exponentials compensate each other and give 1 zeroth order polynomial. If it is first order, it gives first order polynomial. If you do second derivative, it gives x squared minus 1. And if one ramps forward, it gives 3x minus x cubed. It's not literally the eigenstates of the harmonic oscillator, but it is very close. And it gives an idea how one can generate the polynomials of the ascending order in the just applying derivatives. Okay, so try to be generous and give us, if there is a chance to give full credit, do it. If no, just withdraw a little. So the stuff here is practicing creation and annihilation operator to the first excited state. In order to make your and my life easier, I remove all constants, assuming they all are one. And we are starting at state number 1, first excited. So linear polynomial times minus x squared over 2. And then one is applying this combination of position derivative with minus and with plus sign, which symbolizes creation and annihilation. So if there is a minus here, so multiplication by x, applying derivative of the product gives 2 terms. And there is an x squared here and there. They add together, and it looks very much like the second step, right? X squared minus 1. If one changes minus to the plus here, then this second order stuff compensate each other, and one arrives back to the ground state, right? So even if there are some mixed derivations, but there is a word that one identifies the creation and annihilation transitions from first excited to second excited to the ground, then just ramp up the credit. So number 4, multiplying the, again, I'm trying to simplify your and my life by removing some constants, maybe not all of them. So, and the question is analyze the product of these two operators. And if one performs it, there will be 4 terms, x squared, second derivative of a position, and there are 2 terms, ddx times x and x times ddx. This is something to look at. We know that after each operator, there is a hidden wave function, right? So this ddx and x will be applied to x, and we remember that one cannot swap their order for free. So the first term and last term stay unchanged. And here, the subtraction of these 2 terms is nothing but the commutation of position and momentum. And if you give an additional term, which just unity operator multiplied by this Planck constant. So, what is x squared? How do you interpret it? Like
a parabola?
Yes, and what is parabola in the context of our course when we are looking onto like energies?
Minimal or maximal value.
But it is called kinetic or potential?
X squared. Kinetic? Kinetic.
No.
Potential.
Potential, right? So it is potential energy with precision up to the constants. And then second derivative is which energy?
Kinetic.
Yes. So we have potential and kinetic, and together kinetic and potential total energy, right? Hamiltonian. But in addition to kinetic and potential, there is one more term, which if you take care of the constants, it will look a little bit different. But this term that originates from commutation of position and momentum explains 0-point energy, explains why energy of the ground state is above 0. So if you see comments that x squared is similar to potential, like at 10 points, if you see that it is similar to kinetic at 10 points, and if you see the like any discussion of this free term, give some other points and just be generous. Done? Okay. In this question, since it is very small points, be aggressive and non-generous. I think generally the class performs really well, but in this simple question, I think we failed. I failed as instructor, we failed as class attendee. You do not need to go into the physical chemistry class to tell us that oscillations are like mass on a pendulum. You knew it before. The question was to find something exotic like molecules in atoms in molecule, like 2 hydrogen atoms in H2 molecule, right? Or oscillations of the conjugated polymer when the charge is injected, or motion of the electric charge in plasmonic nanoparticles or in plasma. So some effects that still obey harmonic behavior, but not as simple as we can touch it by hands. So RC contour, capacitance, inductivity for radio. The normal mode in laser, like oscillations of electromagnetic field, right? It's also harmonic oscillator. Vibrations of solvent. So let's give 2 points for each example. So whoever gets 5 or more gets full credit. If you have like 1 or 2, it will be a little less. And I think it's just a little signal to look around broader, but it will not affect your overall grade, right? Okay. Extra credit, 40 points. So if you, I was surprised. I don't know, did you use computer algebra or looked into the tables? When I was taking this integral myself, it took like an hour or 2. And everyone just writes first line and then the last line as it would be simple. But I cannot criticize if there is a right answer, if it's correct. But even if the answer is wrong, but you see intermediate steps, try to give some credit. So when chops this integral into 3, 0th order square root of pi, first order we do not care because it is not coming here. And then second order 2 square roots of pi, fourth order 3 square roots of pi, and one adds and subtracts, one gets what is needed, and then one solves for m2 and gets square root of square root, right? Okay, and please add together all grades, and I will just look onto Google Docs and go forward. Let me check line with Spencer and Connor. What is question 6 worth again? It's worth of 40. Maybe it's too many. I noticed how easy everyone writes the answer, but I cannot take my word back, at least in these circumstances. Okay. Are you done? Okay. So basically, now you can lean back and relax, and I will entertain you. No activity is needed. Well, I will give a little, I wouldn't say, maybe a little negative surprise by announcing new homeworks, but it's rule of the games. But they're not due tomorrow. You have time for it, and then I will just entertain you telling stories about the independent research projects. So several class attendees noticed my error on I'm not competitive in arithmetic. I cannot count homeworks. So the one that you just completed and graded was ambiguous, either 6 or 7. So let's count it as 7. Then the next one will be 8. And let's plan to submit it on Monday. Right? I will try to give as much as possible materials to have it completed on Friday so that you can do them from the weekend. And if you find it challenging, please send me questions. I really enjoy answering them. And for this homework, I have like materials that I would otherwise print and distribute, like sections from excerpts from books and some ideas that can help. So if you need additional materials, please let me know. I have them. I'm just not sure if anyone needs.
Can you just send them to the class in like PowerPoint?
I will forget.
Sounds good.
Please remind.
Will do.
Thank you. Okay. And this is not the whole story. We have quite intense time. There is homework 9, which will be due in a week from now, next Wednesday, but it will be kind of lab report based on what we are going to do in the lab today. So if you just record, make copy paste of the screenshots of what you do in today's lab, it will be completed homework 9. And the question there is inspired by our previous discoveries for particle in the free space. So if an electron is injected into auxiliary space when we do not have any ions, when there is only one electron, what does happen to the width of the distribution for the electron? Does it get narrower or something different? What is happening to the, like if we prepare like free space, we inject electron and we make sure that it is initially in a Gaussian shape with certain width. What would happen to this width with time?
Get wider?
Yeah, get wider, correct, expand. Can you imagine it is getting narrower? There is a very quick answer.
No.
If, okay, in regular normal conditions, no, but mathematically, one can immediately get it. How?
Changing the boundaries.
In free space, there are no boundaries.
Freezing it?
No. Regular, like science fictions. What is the most typical apparatus in science fiction?
A laser.
No, it's not a fiction. It's we all have laser pointer. Something that is
Time machine.
Exactly. So if one flips the direction of time, then instead of getting wider, it will get narrower, right? So mathematically, the solution exists. Now, let's check if this conclusion about continuous expansion on the width of distribution, which means it becomes less and less certain, right? Can we apply the same analysis to the particle in harmonic potential, which is typically an atom on a bond, like a ball on a spring, as some of you mentioned in the homework. So if you have distribution for this atom to stay closer and further, will this width increase, decrease, or stay the same? Or there are some additional conditions to it? So, huh? No idea? For me too, I wouldn't intuitively answer, but we have all tools to make little science of this case. So we are going to take the code, do same as Tim Burns did in the very last slide of his presentation, just apply it to harmonic oscillator, and then play with initial width, trying it at a different size and see what would happen to it. Just track the width as function of time. And basically, we will report observations as a like web report or homework number 9. And to exclude unnecessary details, we will set up position right at equilibrium and momentum equals 0, so that we look only at the width. And basically, those questions are lines how to arrange the report. And by following Tim Burns, just uncomment stuff and put potentially close to this. Okay. Now lean back and relax. And if anyone needs this part of the lecture, I can send it, but it's a huge file. It gets through. It doesn't get easy through the email, even if one uploads it to the OneDrive or Google Docs. So here is the sign-up list. Maybe today is a little early, but Friday, very soon we will fill it. And the idea is to apply skills accumulated into the course to a realistic problem. If you are already doing some research and you have an idea how to formulate a problem that can be addressed by physical chemistry tools from the class, go ahead. Just do not listen to me and formulate the stuff. If you're not sure yet, you can listen to me and make some connections. Or if you're completely unsure, you can just single choice of these multiple options. I will go through options and you select and I'll help to all of them. So I will go over the whole list, and I'm trying to update it every year. And also, I'm not active in the Blackboard, but at the very beginning of the course, I did upload the reports on those projects from previous years. You are very welcome to look through and learn their stories of success and failures, repeat success and avoid failures. So there, we do have a code that solves everything related to one-dimensional quantum motion. Now, we can apply it to different classes, two classes of problems. So one can think that our X is position of electron. And then the potential will be like attraction by atoms, right? And we can think how the electron moves through the molecule or through the period. And there will be examples that I will cover. Another option, if the coordinate is position of an ion, like carbon somewhere in the molecule, and then it will have a potential like harmonic or something similar to harmonic, and you can explore how it moves or how it takes different quantum states and see like maybe Raman experiment or stuff like that. So it's another chapter. The next option is when one makes a hybrid of A and B. And this is one of the directions where people are constantly getting prizes and accomplishments in science if one combines these two things. So making the problem two-dimensional with one dimension electron and another dimension is nuclear position is too complicated. It is doable, but not for in limited time. But what one can do is to understand that for electronic motion, system can be in either one or another eigenstate, right? And then we keep the position as nuclear coordinate. And then we have potential energy for one electronic state, for another electronic state, for different electronic state. And then if there is a chemical reaction, there is a simultaneous motion along nuclear coordinate and transfer between different electronic states. It's quite standard approach to so-called electron transfer problems. Okay, another option, angular momentum for rotation. So one can try to look onto quasi one-dimensional circular motion in the Bohr model. So it's not the simplest, but it's quite simple pedagogical problem. So it doesn't have very much of scientific value, but it helps to understand background. And if you foresee that you may have a teaching career in the future, it is a really good choice. So it is the movie that you generate can be always demonstrated at the very beginning when you need to explain something important progress, as you saw me doing it at the beginning of the class. NMR for induction decay, I will cover it. It will use very different code, not the one that we used. You can share it, and one of the attendees of the class last year did it. It makes connection to real life to NMR, but it is you need to be quite independent to go into this direction, not get the whole. Okay. Electron-hole interaction is, or polar-on electron to nuclear interaction in soft materials is cool, but if anyone is hungry for new stuff and this doesn't satisfy your curiosity, I can offer something. Okay, so what will be offered from me right now will be very disorganized. I didn't find time to make it. It's not like a formal presentation for evaluation of my performance. It's only some directions of thought. And they only needed to launch your imagination and make sure that you can select where your brain and heart are on this table. Maybe next time. So I will show some ugly hand drawing, maybe some movies, but it will be not like well set up, organized. So you just need to decide what seems interesting in the result. And here is a recording of similar meeting from one of the previous years. Okay. If we do have electron and we apply electric field, then potential goes with slope, and it corresponds to electrochemistry when the molecule is between electrons. So one can model reduction and oxidation. And it is quite easy. It's naturally added to the code. One just adds slope, first model of the molecule with few minima, and then adds slopes. Or an conjugated polymer. No one selected it yet. It will be very unique, but it means after electron distribution reorganizes, it changes position of atoms and changes the potential. Amorphous materials, if you have a very large collection of, let's say, conjugated polymers or other materials, they will be bent and kinked randomly. And even if it is like ideal conductor with almost no potential or regular potential, there will be regular traps and oscillations of the potentials, which is a quite standard thing. For making our computers substantially more powerful, we of course can use quantum computing. So one of the simple problems related is to put two Gaussian profiles into one potential and see how they what they do to each other. So it is superposition of two quantum states and related to the concept of Schrödinger cat that you can find it online. It's like fun concept. Electron transfer can be modeled in several potentials, or even with one potential, like reactant and product. And there are ways to model complicated reactant product in barrier. It's basically most independent and creative part when you create a potential. Then the code works for you. Ramping the oscillations in the infrared laser irradiating the mode. This means that the parabola, which represents potential energy surface, is superimposed with a slope, which is electric field, which is changed from positive to negative. And it will correspond to parabola goes forward and down, and it will give the start was from ground state, and then it ramps up to excitement. So basically, modeling infrared laser irradiating the moon. The Marcus theory, I think it is maybe a balance between making project for grade and setting it up as a seed for competitive and publishable research in the future. So-called Marcus theory, when you have several potentials for different electronic states, and the nuclei are moving differently depending whether the system is ground, excited, neutral, or charged. And there is a little addition to the code that we work on the labs that catches this stuff. And it was done several times in the class, applying it to different objects. One of the examples of charge transfer is ligand to metal charge transfer, metal to ligand in organometallic complexes. This project is kind of done, but since I have a slide, one of the graduate students in my group is doing this semiconductor quantum dot covered with ligands and places a transition metal doping inside. When one introduces transitions between the electronic states of this dopant, the nearby ions are getting attracted or repelled from it, and it changes the interatomic forces, and then it hits spectral signatures. And if one is going into this direction, it is a bit of slow preparation to inorganic chemistry, which some of you may have to take as part of the curriculum, or like octahedral splitting and different stuff. This is just a movie how electron and hole in the semiconductor are moving in two-dimensional space. And these results are computed ab initio, which is next chapter in the PChem curriculum. But one can extract this data and use it for modeling. So again, about polarons, which are important both for for several areas of material science, including conjugated polymers, but like quantum dots and other materials as well. One does have several potential energy surfaces, and they can be projected onto one dimension. That typically it's more than one dimension. So the surrounding ions follow the change of charge in the atom of choice. So here is a metal organic complex that is being irradiated by light continuously. As time passes by, there are more and more quantum of electromagnetic radiations emitted, and the energy pumped through laser radiation pumps the energy and breaks the metal to carbon hydrogen to carbon, and later on carbon to carbon bonds. So it can be considered as metal ion serves as a catalyst for getting rich hydrocarbon chemistry. So the initial pattern and final pattern of this hydrocarbons is way different. And this initial calculations, which are, by the way, agree well with experiment, can be projected into the language of potential energy surfaces and overcoming the barrier. There is a postdoctoral associate who is doing this research and will be helping whoever's aim on this project. So it was fragmentation of molecules on smaller pieces. Another thing which can happen upon light irradiation is polymerization. When two standalone things upon radiation get more loose, get rid of their capping agents. So it is a silicon and hydrogen, similar to hexacylate, and upon radiation they polymerize and form some network. This can be also translated onto the language of potential surfaces, modeled by the tools from the class. This is something very new that no one did. 3 weeks ago, there was a publication in Nature, which is one of the top journals, that you know what's the order of H2S?
Order what?
Order of hydrogen sulfide.
-2.
Not order, but odor, like smell.
Oh, stinky.
Yes. Yeah. So, but it's not only stinky. So when we build electric circuits for transferring power or for doing computers, the energy of electric current is always lost to heat, right? Therefore, one would benefit if this losses to heat would disappear completely. This is available in regime of superconducting. So some materials do not lose energy into heat when current goes through them, right? But what is the main condition for superconductors?
Cold.
Right. Do we know room temperature superconductors?
Something was just published about them.
Again, excellent. Yes, it was not available until like 3 weeks ago. And typically, the conductors are like metals or some yttrium oxides with complicated structure. But to the surprise, the recent room temperature superconductor is made of this stinky stuff. So when it is pressurized about a million times bigger than in the tire, they form a crystal and start conducting electricity without losses, which is kind of cool. And it's not the whole story. The way how this H2S is prepared in the experiment, if they just take it from gas tank and compress it, doesn't work. They take coal, sulfur, and hydrogen, press it in the chamber with a transparent lids and irradiate it with laser intensely. And then it forms what is needed. So one can, so most stable isomer of sulfur is S8. And upon laser irradiation, you can follow how it breaks this SS bond, and then the hydrogen gas, which is just not shown around, as we go through the simulation, it sticks to sulfur and will create this H2S. So this modeling also can be converted into the language of potential energy surfaces and modeled as part of the class, giving really great seed for competitive in the global scale.
Is that in a methane atmosphere?
Yes. Catalytic reactions or combustions, it's just going from product is a barrier, and the difference is like what is it endothermic or exothermic? And the catalysis is the goal is just to make the activation barrier lower. Okay. So
engine arm is S. Okay, I'm going to get the pro. 99, proceeded, 3, 2, 1, ignition. Right away, Houston. That's your good. X5.
so what is shown on this slide? Is it fiction or is it real?
Real.
Okay.
Yeah, it's real.
Then you are on the there is a controversy. Some people argue that it was set up in Hollywood. So which what is it?
Lunar landing, taking off of the man.
Yes. So in order to reignite the fuel and oxidizer there, when we drive cars, like oxidizer is oxygen from air, fuel is like octane from hydrocarbon from the tank, and we use spark plugs. But sometimes they have misfire. If it is like a multi-billion program with humans risking their lives, misfire is not acceptable, so one needs to minimize the risk. And there is a way to make fuel.
Pipette is there for a reason. I don't want my hands anywhere near this thing. You can really see there is this very fast reaction which generates loads of nitrogen and also ethane. And so all of the products here are gaseous, and you get a tremendous expansion. At the same time, because it gets very hot, it glows so brightly. And Polypipette is there for a reason.
So it is the mixture which is used in situations when one do not want to risk spark plug. One just have a few oxidizers self-ignite when you pump them into the chamber. And it was used for Apollo mission, and it's still used in space programs. So here is the fuel, hydrogen. Here is the other derivative of hydrogen. And oxidizer is nitrogen, dinitrogen tetroxide or nitrogen dioxide. And one can model how they interact with time. And the main process that launches the ignition is hydrogen being pulled from the fuel to the oxidizer. Here is a little slower motion of this hydrogen goes to this oxygen this time, and this reaction has a barrier, which one can extract and model in the class or do something similar. So the challenge in this little research was that the height of the barrier is much higher than temperature on the surface of Moon or even at the surface of Earth. So if it is true, the barrier is so high, then one needs to heat the mixture to 3000 Kelvin before it ignites. So if this correct, if this calculation is correct, then lunar mission was failed. But if one brings up, here is a bit more for dimethyl hydrogen. But if one brings up this hydrogen will stick to this oxygen. So there is a paradox, seemingly paradox situation that if one takes into account that the proton is not a point charge, but the wave packet with certain bits, same as we do now in the class. Then one can get the probability for this proton to go over the barrier, even if the energy is below the barrier, so-called tunnel. And then ignition is possible at temperatures lower than the height of the barrier. And this calculation proves that lunar emission was real, which you believe anyway. So I think for the sake of the time, we need to depart, but I'll continue the story when we meet next time, and you will be better prepared to make the solution. So meeting is done. I'm staying here to answer any questions, but everyone is welcome to disconnect or to depart. So looking forward to see you in the lab, where we will contribute the efforts towards cohort number 9. Perfect. Thank you. Thank you.